1897, while working with the Crookes discharge tube, Thomson determined the charge-to-mass ratio of cathode rays and was given credit for the discovery of electron. And he came with the first model of atom in 1903 that we call plum pudding, where the electrons were distributed evenly throughout a homogeneous sphere of positive charge. So you could see positive and negative charge together. In 1911, another experiment was used by Herbert Millikan to find the charge of an electron. So they used this experiment where created microscopic, you can see over here, we have an atomizer that will should just spill some oil over there, creating microscopic oil droplets which are electrical charged. These drops could be slowed and reversed by electrical field. So when this coming out, so the velocity that we're coming down over here was getting slower because we have radiation over here. So by measuring the strength of the electrical field required to how the free fall of the drops, and by figuring out the mass of the drops themselves, Millikan calculate the charge of each drop. So Thomson, when he used the cathode rays experiment, found that the particles that compose the cathode ray have the following properties. They travel in straight lines. They are independent of the composition of the material from which they originate, the cathode. They carry negative electrical charge. Okay, so when Thomson measured the charge mass ratio of the electron to be 1.76 times 10 to the 8 coulombs per gram. In 1906, Ernest Rutherford, a former student of Thomson and his student Hans Geiger, found alpha particles at thin gold foil. If a plum pudding model of the atom was correct, alpha particles should pass through undefectedly, right? However, what happened over here, that some alpha particles were deflected. Exactly, imagine if you are holding a paper, a very thin piece of paper in front of you, and someone shot you. So the bullet came to the paper and was deflected. That was like, oh, what happened over here, right? What do we have there? So what we have there is, okay, negative charge was deflecting that. So positive charge. So we have a nucleus, right? Because most of the alpha particle pass through the foil because an atom is largely empty space. At the center of an atom is the atomic nucleus, which contains the protons, which is a positive charge over here, right? So the alpha particles that bounced backward did so after striking dense nucleus. So then come and was deflected, like here. The other could pass just because atom is largely empty space. If you feel like empty inside, just think about it. You're made by atoms, a lot of empty space. So Rutherford had discovered the atomic nucleus and proposed a new model of the atom. So now we have the nucleus, and around there we're gonna find the electrons. So have protons and neutrons and the nucleus. That is the other model. So based on the massiveness of the nucleus, Rutherford predicted that it must contain neutral particles in addition to positive charged protons to stabilize the atom. So neutrons were discovered by James Cogovac in 1932. So now our nucleus was completed, positive and neutral particles. So if you are interested more in the history of the atom, you can press pause in your video, and you're gonna see the theories and the models of John Dalton. So you have solid sphere model, Thomson with the plum pudding model, and then Ernest Rutherford, the nuclear model, Niels Bohr with the planetary model, which I love it, and I'm gonna use a lot during our class to explain to you, because it's the most easy way to explain the distribution of the electrons around the nucleus. So, and then we have the quantum model by Erwin Schrödinger in 1926. Okay. So the subatomic particles, we have electrons, protons, and neutrons. Outside of the nucleus are the electrons, and the protons and neutrons are inside of the nucleus, right? So we have our nucleus over here, and around that we have the electrons. See, again, I'm using Bohr model. Remember that I said, like, I'm gonna use the Bohr model a lot. So we have a charge. So the electron will be negative, proton positive, and we have no charge for neutron. Okay. Each element has a characteristic number of protons in nucleus. This is the atomic number. The total number of protons and neutrons in the nucleus of an atom is the mass number. So mass number will be protons plus neutrons. So we have the symbol of the elements. Remember, the first letter must be caps letter, and this is the lowercase. Uppercase and lowercase is the second letter. Most of the some elements we have just one letter, one symbol. Okay. So we have the mass, protons plus neutrons, the atomic number of protons. An example here, the element is silicon. So we have 14 is the atomic number. So it has 14 protons. The mass is 29. So I can find easily, knowing that the mass is proton plus neutron, since you have the mass, which is 29, and you have a proton, which is 14. So it will be 29 minus 14, and we have 15 neutrons. Okay. So just pause and do the same over here. Tell me number of protons, atomic number. I want to know the mass, and I want to know the number of neutrons. Can you do that by yourself? I encourage you to pause your video and try by yourself. Okay, so protons, electrons, mass number, and neutrons. So we have 6 protons, so that is atomic number. We have 6 electrons, because in a neutral element, the number of protons will be exactly the same number of electrons. Okay, so if you have 6 protons, I'm gonna have 6 electrons, unless you have a charge. Okay, that will be different, and then we're gonna talk about that later. Mass number, so it's 12. So 12 minus 6 is 6, so we have 6 neutrons. And remember that I said the postulate, so we can have a different mass. So atoms of the same element that have a different number of neutrons and the nucleus are called isotopes. So isotopes have the same atomic number but different mass number. Okay, so they have all 8 protons because they are oxygen, but since we have different numbers of neutrons, 8, 9, and 10, the mass number will change. So these were called isotopes. We have many elements that exist as a number of different isotopes. Very not stupid example, but it's a very simple example. If you go to Publix or other, we're gonna find different types of orange or different types of onions, but they are still onions, they're still orange, they're still apples, but they have a different, they are different, right? So with carbon or hydrogen, so they will have a hydrogen, they will have a different mass, but they are still hydrogen. Okay, so what is changing here is the number of neutrons, and they always call used to represent like hydrogen 1 or hydrogen 2. That means I have isotope with the molar mass 1, the mass 2 for this one. Okay, that is isotope, how you represent. So like here, carbon 12. So I know the mass is 12. So we often refer to isotope by starting the name of the element followed by the mass number. Okay? So the atomic mass is the weighted average mass of all known isotopes. Now we understand why I'm talking about isotopes before atomic mass, because the atomic mass is the average. But how you calculate this average? So here I have boron 10 and they have boron 11. Look at this. The bottle over here, so it would be 811. That is the boron. Okay? So the boron that is the mass, the average. How they do is 10 plus 11 divided by 2? No, right? Because that would be a simple average. We need to take in consideration the availability of each one. 20% that we're going to find on Earth is boron 10. 80% will be boron 11. Okay? So like here, gallium has two isotopes. So I have gallium 69 and I have gallium 71. So to calculate this, and they give us the abundance of those two. 60% what you're going to find is 69, and 6%, 39.89% that you're going to find is gallium 71. So to do the average, you need to take in consideration the percentage. See? So divide by 100, so we have a 0.6011, and here divide by 100 because you need to take out the percentage. You have 0.3989. Okay, so then you can multiply each mass by the percentage and add together. So you have the mass, atomic mass unit. So AMU is atomic mass unit. Okay, that's the way that you're going to calculate. So we can use the periodic table to obtain the atomic number and atomic mass of elements. So we have atomic number and we have atomic mass. All the informations are there. So another thing that some people ask me, okay, so we have isotopes and we have so hydrogen isotope. So we have hydrogen, we have deuterium, and we have deuterium as well. We hydrogen free. So but here. Some students ask me, why is it some books the D2O? Is this water? Yes, but we call heavy water because we are not using the hydrogen. We are using the hydrogen isotope that has 2 as mass because it have more neutron. It's slightly more dense than lighter water and has a slightly higher melting and boiling point also. Normally use heavy water in nuclear reactors to slow down neutrons released during the fission process, and there's some equipments that we use. Okay, that's it. That's all for now.